Hello, everybody. Good morning. It is Thursday, April 16th, 2020. And today, I want to cover that Google form I assigned you guys yesterday on Wednesday, as well as the IXL assignment that I am assigning today. So, this is a little bit of a longer PowerPoint, so I do kind of want to keep up the pace during it so the video is not too long. I do think I'm pretty proud of what I put together. I think it'll be very helpful if you tried your best on the assignment yesterday. Okay, let's talk about the first question here. So, for the following equation, what is y when x is equal to 4? Well, you go ahead and you plug in 4 for x right here. And this gives us a new equation. Y is equal to 3 to the 4th. So we want to find out what y is when x is 4. So we have to go ahead and find out what 3 to the 4th is. Well, 3 to the 4th, that's 3 times 3 times 3 times 3. We do that 4 times, right, because we have a 4 in the exponent. Break this down into pieces. We know 3 times 3 is 9. Then we know this 9 from here times this 3 is 27. And then we take this 27, because that was all 3 of these, and then we times it by this last 3 here. So 27 times 3, this gives us 81. That's what we have here. So when x is 4, y is equal to 81. If you went ahead and graphed this, that means when x is 4 down here, you're going to have a point all the way up at 81. So this should just be another example of how fast exponential growth is. Because we know when x is 0, and you do 3 to the 0, well then y would be 1. So this would be a point here. So this is going all the way from 1 to 81 just when x moves over 4, increases by 4. Right? Remember, this is our x-axis and our y. We'll talk more about graphing next week, but it is something to keep in mind. Alright, this next question looks a lot harder than what it is. Whenever you see a question like this, you know I'm not trying to trick you guys too often. You should know that there is probably an easy way to do it. So if you just follow your steps, you can go ahead and find out what y is when x is 0. So to do that, plug in 0 for x. So we're going to plug in a 0 right there. That's how we get this here. This number here, it doesn't matter what this is. Anything to the 0 power is 1. So this gives us y is equal to 1 plus 1. That's what I have written here. Well, 1 plus 1 is 2. That means when x is 0, y is 2. So on the graph, that would be our y-intercept of this exponential. We'd have a point here, and then it would do the normal exponential stuff. Actually, it would be flipped around, but we're not really too worried about that. Either way, it's exponential, and that's what matters. And you don't need to know what the graph looks like. We just need to know what y is when x is 0, and that was 2. So 0, 2, we saw that was on the graph. Alright. Does the graph below show exponential growth, exponential decay, or neither? Well, you see as x increases, so x is increasing in this direction, right? X is getting bigger as you go this way. Well, we see that the graph is rapidly shrinking towards zero. Look how fast it goes towards zero. So it's going really, really fast at first. It keeps, maybe it's cutting in half or some number, right? It's reducing by the same amount over and over and over and over again. This is obviously not growth, right? Because growth would be getting bigger. This is getting smaller, so this has to be decay. And it is exponential. We already talked about that, so can't be neither. This has to be the answer. Alright, for the following equation, what is y when x is 2? Well, again, we plug in this 2 for this x here, and we get y is equal to 2 squared plus 4. Well, we know 2 squared is just 2 times 2. 2 times 2 is 4. Y is equal to 4 plus 4. Well, that's 8. So when x is 2, y is 8. Remember, this is giving us a coordinate. This would be on the graph of this function here if I asked you to graph it. Just like when you fill out a table of values. Alright, this was probably the hardest question on here. I wanted to see how you guys handled it. So, let's take a look. We have 5 to the x times 5. And now I threw in a little curveball here. I said, well, what about if x is negative 2? Well, you go ahead and plug it in, and you get 5 to the negative 2 times 5. So, this negative 2, whenever you see a negative exponent like that, that should always be raising a red flag for you. We can get rid of this negative, make that go away, by bringing this down, taking the reciprocal of this number here. Right, so we're turning 5, we're bringing it down to the denominator, and we're going to square it down there. Now it's a positive 2, and it's just 1 over 5 squared times 5. Well, next step, 5 squared is 25, so we have 1/25 times 5. And remember, 5 is really just 5 over 1. 1 times 5 is 5. 25 times 1 is 25. 5 goes into 25 one time. 5 left over. Right? This last step is just simplifying a fraction. Divide these both by 5. So again, this is probably the hardest question on here. Just take a look at this slide. We'll have to talk a little bit more about negative exponents, I think. Just remember, negative exponent, like if we had something like 2 to the negative 3, it's the same thing as 1 over 2 to the positive 3. Okay, so you get rid of that negative by flipping wherever the 2 is. So if you had something like this, 1 over 2 to the negative 3, well, you can do the same thing, it's just the other way around. You bring this up to the numerator now, and we turn this negative exponent positive. Alright, so what grows faster, exponential growth or linear growth? If you were paying attention in the last video, I did talk about this for a little bit. Exponential growth is always going to be faster than linear growth as x gets bigger. And if you give it enough time, or if you let x get big enough, exponential growth will always pass linear growth. Right? Because this is always going at the same rate. Right? The slope we know is always the same for a linear graph, but we know for an exponential graph, especially exponential growth, the slope is always getting bigger. It's always changing much, much faster. It's rapidly growing. Right? So this curve here, well, if you let this graph go on long enough, this curve, the fact that it curves upwards, means that it's always, no matter what, going to pass this straight line, this linear graph. Right? This is always going at that same rate. This linear graph can never start curving like an exponential graph does, so it can never keep up with it. Right? It can't do that. All right, so this next question here, this is something we'll definitely talk more about, but I want to see if you can think through this. You do have the information to solve it at this point. You just need to be careful. So imagine that there's 100 deer in a nearby wooded area. Um, we know that every 4 years, those 100 deer, that population, that's going to double times by two. So we know after 4 years it's going to double. So after 4 years, this 100, we times it by 2, we're going to get 200, right? Because we double it. And then, but we want to know after 8 years. So that means it's going to double again, right? Because we have the first 4 years, and then we have another 4 years to get the 8 years total. So it's going to double again after 4 more years. This 200 is going to double, and it's going to give us 400. And if I asked you for 12 years later, well, you would double this 400 and go to 800 deer. And you would just keep doing that. But that's something, again, we'll talk about more, but hopefully you're kind of getting the idea there. Now, this is another example of a question that we're going to explore a little bit more um, later in the unit. Is the following an example of exponential growth or decay? Your savings in the bank increase by 2% quarterly every 3 months. Okay? So, these numbers aren't actually realistic here, but what this is saying is that if you have money in your account, after 3 months, it's going to increase by 2%. Okay? So 2%, if it's increasing by 2%, it means we're really taking 102% of what we have in our account. Right? If you had $100 in the bank and you know you're going to get 2% interest every 3 months, well, that means that your $100 is going to turn into $102. So it increased by 2%, but it's really 102% of what you had to start. Right? You had $100 at the start, so 100% of $100 would be $100, and then we had that extra 2%. So 102%, this is actually, this percentage is actually can be converted to a fraction. It'd be 1 and 2 over 100th. And it turns out that this is actually just our growth factor in this case. This is our base, and then we have our exponential here. So we'll have to talk more about percentages and everything like this, but um, either way, if you don't understand what I was talking about here, you don't really get it yet. That's okay, but you didn't need to know all this. Really, what you needed to answer this is to know what growth or decay meant. Well, we know your bank account savings are increasing. Whenever you see increasing, you should always think of exponential growth. Okay? Decay, this would be decreasing. a little messy, but I want you guys to see it. Okay, so exponential decay, decreasing. Right, we have that DE at the start. That's a way to remember it. Grow big, you're getting bigger. Decreasing, decay. All right. So is the following an example of exponential behavior, linear behavior, or neither? Well, this one, we haven't talked about this too much yet, but this is a quadratic function. And notice that this graph is different than the others. It's creating this kind of U shape here, this valley, if you want to think about it like that. Well, think about if you had somebody walking from left to right through this valley. Well, they're going to be going downwards, 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 and then upwards, upwards, upwards. We know exponential growth always went upwards. And exponential decay, we always saw that go downwards, decreasing, right? And linear, well, we've talked about this a lot. Linear graphs are straight. So this is linear, exponential growth. This was exponential decay. Well, this quadratic graph looks nothing like this. But maybe you looked at this in a different way. Exponentials also only have an x in the exponent, right? Or they have a variable in the exponent. You can have other numbers with it, but you do need that variable up there. Our x is down here. Right? We have an exponent, but our x isn't in it. So this is called a quadratic, and this is different than an exponential. Right? Remember, exponentials were things like y is 2 to the x, where x is up here. And then finally, this is just review from the IXL this week. What relationship does the table below show for x and y? Well, if you go ahead and you look at how x and y compare to each other, you see that as x is getting bigger, y is increasing by 5 each time. Okay. So this would be linear growth because we're adding the same number over and over. Remember this number here that we're adding up over and over, this would be our slope. So this graph would be something like y is equal to 5x, and then whatever the y-intercept would be. So this is linear. And if you wanted to test if it was exponential, remember you could, another way you can do this is you can take you should see that if you multiply the same number over and over again, then that would be an exponential. But this is linear, we're adding the same number over and over, so if you want to know more about that, take a look at some of the videos I made earlier this week. Okay. So I do have a few examples for the IXL today too. Just so you know what you're going on, because there is something a little bit of a curveball with it, something a little new, but I think you guys will all pick up on it just fine. This is called a function rule. So what we're trying to do is trying to find something called f of 4, right? And what all this f of 4 is, this is really just a y, the same thing as y, but it's y when x is 4. It's the same thing. So this is really use the following function rule to find y when x is 4. That's how you could read it. If you don't like this, well, just swap it like this. Okay? So this is telling us that we're plugging in a 4 here for x. We'll see that in the next slide. If you want to try it now, you can go ahead and pause it. Plug in a 4 for x there. Okay. So let's take a look. Already kind of talked about what we were doing here. We plug in this 4, this orange 4 goes to our exponent, right? Because that's where x is. Our x is in the exponent. We're plugging in a 4 for x. Right? Whatever's inside these parentheses here, that's what we're switching for x. That's it. So we're switching a 4 for x. That's what we put here. 4 times 4 times 4 times 4. Remember that's 16 here. 16 times this 4 be 64. And then we would have 64 times this last 4, and that would give you 256. Okay? So this means that f of 4 is 256. Now, what this means, in terms that you're used to, is that when x is 4, right, we swapped a 4 for x, y is 256. And that also means that 256 is on the graph. And so this is some exponential. We know that when x is 4, y would be 256. Okay. That's the same idea for all of these. Use the following function rule to find f of 2. Well, go ahead and try it on your own first. Pause the video here. Welcome back. So you should have plugged in a 2 for an x right here. Let's see what that would look like. Excuse me. Let's see what that would look like. Okay. Use the following function rule to find f of 2. F of 2 means we need to find y when x is 2. So we swap a 2 for that x. Right, so we put a 2 right here. Now we have 10 times 2 squared. Well, 10 times 2 squared, you can kind of rewrite it like this. Maybe that looks a little more, something you're a little more comfortable with. We know that 2 squared is 4. 10 times 4 is 40. So this means that when x is 2, then y is equal to 40. The coordinate 240 is also on the graph. Okay? But this is what we're actually solving for on the IXL. This is what it's asking for. And then this down here is what it actually means. Alright, so we got our last slide here, or the last question here. Try it on your own first. You can go ahead and pause the video here. Okay, welcome back. So you should have went ahead and plugged in a 2 for x right here. Let's see what that looks like. Alright, you plug in a 2 for this x. That means we're going to switch this x with the 2. that's what we do over here. So now we have 12 squared instead of 12 to the x. So we have 10 times 12 squared minus 1. Remember, when we don't see any addition, subtraction, or anything like that written here between these, that means you go ahead and multiply. It's a star there. Okay, so we have, let's rewrite this so it looks a little nicer. This is really 10 times 12 squared minus 1. We know that 12 squared is really 12 times 12, and that's 144. 10 times 144 minus 1. Well, to find this, we're just multiplying by 10, so you can just add on a 0 to the end of this. Right, we just add on a 0 to the end. You're multiplying by 10. And then we just subtract 1 for that. And that leaves us with, oops, that's a little bit of a typo. This should be a 1,439. So when x is 2, y is 1,439. Okay, so I hope this all was really helpful for you. If you have questions on it, you're still confused, please let me know. I'm always uh, I'm always looking for feedback. It's kind of hard because I'm not, there in class with you guys answering questions. So you got to keep letting me know. I'm always happy to hear from you guys. So please, whenever you have a question, or even if you just want to say hi, don't be afraid to shoot me a message on Class Dojo or Google Classroom. You know, I hope you're all doing well. So take care. Have a great rest of your day.